Morning, folks. There's a lot of discussion that's been going on the last few afternoons in lab about optimization for drawing and computing intersections and so on. Wanted to talk about a little bit about that. And but first, any questions about Lab 3? There is a code snippet on the framed SPI section of the SPI page that shows how to open a SPI channel in framed mode. What was pointed out to me today is that it is incomplete, and that is because this is the part that has to change. It's not the whole code. If you just write this, nothing will happen because SDO is not attached. And so, if you're going to copy and paste code, I suggest doing it from the example code, which does have all of the setup in it. So, you open the channel, you attach the modified chip select, and you of course have to attach RPB5, which is the output. But are there any questions at this point about Lab 3? You will find that the most time-consuming part of the loop, of the inner loop, through this code is, anybody want to take a guess what it is? What the most time-consuming operation is in the ball update loop? It's drawing the balls and erasing the balls, because you're cranking a bunch of transactions through an SPI channel. It's running at 20 megahertz, but it's still reasonably slow compared to lots of other operations. So optimization of the drawing may well speed you up more than fiddling with minor optimizations of the math. In particular, you draw a nice big fat ball of radius 4. It's going to be something like 4 times 4 times pi over 4 pixels. It's going to be something like 12 pixels. You drop the radius to 2, goes down by the square. Now you're looking at 4 or 5 pixels. So smaller balls are going to draw faster by a lot. Furthermore, if you go into the TFT, now this is down in the, this is how I spend my life, going into the weeds. In the TFT gfx.c file, you will find the code for drawing a circle or a filled circle. And they're using a good algorithm for that. It's called a Bresenham circle drawer. But it still requires a fair amount of calculation to figure out where the next point is, because after all, you have to do something like take the square root of x squared minus some constant squared. And so you will probably be able to draw a ball or erase a ball faster by building an inline that hard codes the offsets of 4 or 8 points or so from a center. So you're going to hard code the offset of some template, say 5 points. That's a fairly crude circle, but nonetheless it is. Say 5 points, hard code the 5 points as a macro, and then feed it an XY coordinate for the center, calculate the offsets as plus minus 1, and stamp that template onto the screen. It will be a good deal faster than using the circle macro or circle function. Did I see a question on your face? Why? You're drawing 5 points. Why should you call circle to draw those 5 points? Just draw them yourself.
You want us to draw like 5 pixels, like individually? Is that what you're saying? Or
Yeah, why not? Because then you're not having the circle algorithm calculate the offsets of everything, which is doing some sort of numerical integration. Right? It's doing it what's called a, here's a term. How many people have heard the phrase digital differential analyzer? Nobody. Right? It's operating a digital differential analyzer, which is a primitive form of numerical integration. And it is therefore slower. If you go into the, can I get to the GFX stuff here? I don't think I exposed, yes, there it is, tftgfx.c. So if we go plowing down through here, oh, the very first thing is TFT draw circle. And so you look at this, and there's a whole bunch of arithmetic that goes on, and then TFT draw pixel with plus and minus the radius and a color. You could just call directly yourself TFT draw pixel. Save all of this overhead of doing all these calculations. And by the way, there's a circle helper which is called within circle and within fill circle to help fill the circle. So there's TFT fill circle, which is what most people are using. It's doing a whole bunch of stuff. Draw fast V-line TFT fill circle helper. Fill circle helper does it has the digital differential analyzer running right there. And then draws a bunch of lines. So you're probably going to be better off to hard code a template and then just stamp it onto the screen in either black or some color.
Okay, but if the radius is 2, then you don't have an odd number of pixels to have a center.
So you use 1.5. You have fixed point. But if you remember, the pixels are small. You won't see approximations very much. But it's easiest just use a odd number. Make it 1.5. Visually 1.5, but for calculations make it 2. Or make it 3, but for calculations make it 2. If it overlaps a little bit, you won't see it.
Got the frame rate set at 15, right?
Correct.
So,
frame rate at 15.
So if you, let's say you keep adding balls and the code isn't as efficient as you should have it to be, how will you know if, let's say I'm printing 50 balls, it works. If I try 60 balls and if it exceeds 15 frames per second, what happens then?
It'll catch fire. Not joking. I hope. So if we go down here to the pseudocode example, at the beginning of this loop, we're using PT get time to get the current time, and then at the end, we're asking to yield for an amount which sets the net time of execution to 67 milliseconds. If this number, if this expression goes negative, you've run out of time. Therefore, for testing, you could print this argument. If it goes to 0, you're out of time.
What happens on the printing of the ball if that does happen?
What happens to the printing of what?
Of the newer balls that I'm trying to print.
The whole system will just slow down. It'll work, it'll just slow down.
Wait, will it wait 0 seconds? Or like will it
Well, what?
like will it just go on the next time?
So, I don't know that I ever characterized what would happen if if yield time went negative. I suspect it does something that is not too nice, like it waits forever, or until the counter overflows or something. I don't remember testing that. I might have tested it. I might have even trapped it, although I doubt it. I think it just fails. So when you're tuning, you might want to print out this argument and find out what its value is. What else? There's some interesting optimizations of the collision algorithm that are possible, which were stimulated by discussion with a couple of students over what happens if the discretization, the fact that you're moving these balls in steps, implies that at some point the balls are almost completely overlapped so that Rij is rather small. And if you look at the update formula for delta Vi, and so if we look at the update formula for delta Vi, and we say we want to avoid this divide by making sure that we just use the collision parameter as if the balls are hard bouncing off each other, then the components of Rij that appear in two places are going to be too small. And in the limit in which you get unlucky and the two balls exactly overlap, Rij will go to 0. So you're stepping by twos, boink, 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 boink. Rij is 0. The delta V calculated is now 0. And the balls keep going through each other. So that says that for 0 Rij, this will fail. Right? Everybody buy that? Yes.
Can we go back and talk about how to avoid that divide?
Yes! Thank you. I was going to say, how do we fix this? So, thank you for the lead-in. Well, there's two parts to this. First of all, the case where the offset is 0 implies that the balls are approaching each other, so that's Rij, in a fashion so that Vij is parallel to Rij. They're coming directly at each other. Not necessarily horizontally, it could be like this, but they're coming directly at each other. Otherwise, you can't get the Rij going to 0. They'll pass, the centers will pass by each other.
Couldn't you have like something like this? Where they pass each other in angle?
Yeah, it's discretized. So I don't see why you couldn't have one coming like this, where their time steps get unlucky and they both end directly on top of each other, even though they're not parallel.
If they're coming at each other like this, it is certainly true that they cannot go to 0.
No, but suppose that that ball's still going like this, but the upper ball is going at an angle down, so that at a single time step will end up on top of each other, even though the velocities aren't parallel.
I don't.
Does that have to be parallel? It's the relative velocity that has to be parallel to it.
Yes, the relative velocity has to be parallel
Okay, yes, that's true.
to the vector.
Yeah, I'm not understanding. You can't have something where they're coming in at an angle, then right when they're on top of each other. Right here.
So you're saying a symmetry like this. So what happens with that? On the next step, this step's there, and that's, yeah, you might be able to get that. And let me see if there's a degenerate condition in there. Let me think about that for a minute while I go ahead with this other stuff. So if they are collinear, then you know that the balls are going to bounce off of each other. No matter what the angle is, they're going to bounce off of each other. If they're coming at each other, they're going to bounce off of each other, and all you have to do is exchange their speeds. VI becomes VJ and VJ becomes VI, and there is no calculation of delta V at all. Now what happens in this case if
Is
this...
RIJ and VIJ actually parallel at that point?
Here, yes, they are parallel. Yeah, so it's the same condition. So in this case, if these hit, VI, it's not delta VI, it's VI, becomes equal to VJ, and VJ becomes equal to VI. You,
It's just like
you-
bouncing off the wall. Basically.
right, you just basically swap the velocities, and I think it works for all cases. So it's easier. You detect the radius is 0, you don't do the delta V calculation. You just swap the velocities. And that conserves momentum too, which is always in good taste. Now you say, well, how much can we let it miss 0 and still treat it as 0 and just swap the velocities? In other words, could we do this for any impact parameter? The answer is no, you can't. But let's say these are almost hitting center on center. Now all we have to do is define almost. And below some threshold impact parameter means closest approach of the centers. Below some threshold impact parameter, you just exchange velocities. Above that, you have to do a better calculation. And so, pull a number out of your nose. What would you pick? Remember, the dynamic range for Rij magnitude squared is 0 less than or equal to Rij squared less than or equal to 16. That's the only region, that's the only region over which there can actually be an impact.
Can we just do like R squared? No, just R is the distance. Because right when that's Rij, that would be like 2R.
So Rij is the relative approach, and that's what you're worried about going to 0.
Yeah.
So that's go.
So we do it. We make the threshold right now for collision just be 2R. Like, why don't we just make it R? Because that's pretty close.
Oh, I see what you're saying. You're saying cut this down from 16 down to 4.
Only for this case.
How about just saying if it's less than 4, if R squared is less than 4, we just impact it as if they're head on.
Yeah.
Or 2. But I like 4. 4 works for me. I like 2 a little better because it's a little closer to head on. But you pick some number. You pick some number between 0 and 16 and say if it's less than that number, you merely swap velocities. You do not do the delta V calculation. You swap velocities.
Why would you swap velocities instead of just not touching them? Because you're going to end up with balls, they have basically the same position, and you're just swapping velocities, so they're going to look the same whether I swap velocities, whether you don't.
That's not true. Let's say this one's going twice as fast as this one. After the impact, this one's got to be going twice as fast as this one to conserve momentum. That's why you swap velocities, to conserve momentum.
Okay, so when you do the calculations for real, they're not close enough that you can just use this trick. Then there's that divide in there. You have to divide by the length of Rij squared.
Mm-hmm.
So if we don't want to do a floating point divided, we can all help it. Is there a way to get around that?
So again, thank you. This was going to be my next breath. And that is, what do we do in the middle range? What do we do if, well, let's say we're going to cut off less than 2 or less than 4 swaps velocity. What do we do then between 2 or 4 and 16? There, the unbiased thing to do, and by the way, you don't want to do a divide by 0, for sure. So this protects you from ever dividing by 0. What happens on this architecture if you divide by 0? Catches fire. Yeah, halt and catch fire, right. When I was an intern, we had rotary mechanical calculators, which did a divide by mechanically shifting a carriage and then subtracting and shifting a carriage and subtracting. And if you did a divide by 0, it ran forever. You had to unplug it. Anyways, and that is halt and catch fire. So what this architecture does is notice you divided by 0 and throws a software exception. It throws a software interrupt, which is referred to as an exception. There is no exception handler written for divide by 0 unless you write it. You haven't written it, and neither have I. Therefore, the system takes a reset. And so the symptom of a divide by 0 will be flashing TFT display. That's obscure. So what do we do? Well, I thoughtfully made a table for you of how long it takes to do various operations. Cycles per operation for add, multiply, and divide for 3 forms. For fixed 16, which is what you're probably using, for float, and for something called underscore accum. All right, push your stack, folks. All right, new topic, but keep the other one pushed on your stack. Float underscore accum, it turns out that this compiler, I found out yesterday as I was reading the new documentation as opposed to the 2-year-old documentation, which is what I had on my website, has floating fixed point built in. It has native support for fixed point types. And so you could specify, just to prove it, I put the table in here. There's a type called accum, underscore accum, which is a signed 16-bit integer, 15-bit fraction. It is within 1 bit of fixed 16. All the usual stuff is supported. Dyadic operators, unary operators, increment decrement operators, assignment operators. The only thing that is not supported is printf and scanf conversions, and so you have to work through a float cast to make that work. Pop stack. Performances of this accumulator is about the same as the fixed 16. The add may be a little faster, the multiply is a little slower, but they're both a factor of 2 between 30 and they're a factor of 30 faster for multiply for add, a factor of 2 faster for multiply, and the same speed for divide, interestingly enough. So you could just take the hit and do 1 divide, which is going to cost you the same as 3 multiplies. 3 multiplies. That's not so bad. And because you're not trying to operate in a region where Rij, the magnitude of Rij is very small, remember you're not doing this operation if Rij, the magnitude of Rij is less than 2 or 4 or something. As long as you're not trying to operate where Rij is very small, you're not going to get killed by round-off errors. And so it should work. Should all work. You actually have to do 2 divides because it's a vector. But you could do better than this if you wanted. you have numbers ranging here between 0 and 16. You could treat those as indices into an array of reciprocals and use the table of reciprocals above 3 or 4, which will get you within 20%, to do the invert instead. Multiply by a reciprocal that you store in a table.
It'll be a big table though.
16 entries.
Well, only if you don't include the fraction.
Exactly. So you don't include the fraction. You take the hit. It's not going to be too accurate. You make the index a little too big rather than a little too small. You make the reciprocal a little too small rather than a little too big, so that you dissipate energy on each cycle rather than add energy. And I doubt if you'll be able to tell the difference. Or you'd make it twice as big and change it to every half integer. Or make it 4 times as big and make it every quarter integer. Or just do the divide. Or ignore it completely and say, if it's less than 2 or 4, do this swap velocity, and if it's above that, just set it equal to 16 and do the shift left 4 bits, and I'll bet you can't hardly tell the difference. It'll be you can't. It'll be dissipative. It'll lose energy faster than it would otherwise, because the effect of not... I need to split screens and put different things on both screens. That would be confusing. It'll be dissipative because now the denominator is too big relative to the numerator, and so the delta V is too small. So you're going to get a little bit of under bouncing, but you probably won't notice that.
What if we force them to be 4, or 16?
Oh, so what if you just take them and say, you stinking balls, and pull them apart? Well, that is equivalent to, remember, what you care about is, really what this is doing is normalizing the length of Rij to 1. Those are normalization factors. And so what you're doing is scaling Rij up from some small value to a larger value, so you're effectively multiplying Rijx and Rijy by the same factor. And really what I'm saying is, if you make a table lookup or you do the divide, that is what you were doing, is moving the balls apart. Now you might be able to do some intermediate thing where if it's less than 4, you just exchange velocities. If it's less than 8, you scale them up by 2, shift left. If it's less than 16, you do nothing. You just shift by the whole 4 bits to simulate the divide. So shift right by 3 bits, shift left by 4 bits. Remember, folks, this is computer graphics. If it looks right, it's right. We're not doing physics simulations here. I don't care if the entropy is correct. In another context, I would care, but not in this context. I want to see a playable game. One of the TAs mentioned that, and one of the students at a TA mentioned that within 2 sentences in the lab write-up, I had put these barriers at 2 different positions. at 1/3 and 1/4. I want the game to be playable. There is nothing that is cast in stone. You don't like a velocity of plus or minus 1.5, you can make it plus or minus 3 or plus or minus 1. You don't like a velocity, an x velocity of 1, make it 1.5 or 2. Oh, that reminds me, numerical tricks for generating random numbers. There is, of course, a rand function which returns a uniformly distributed pseudo-random number between 0 and, anybody know the answer to this one? It actually depends on the implementation of the C compiler. In this case, it is a short. So it's between 0 and 65,536, 2 to the 16th. If you merely took those 16 bits and copied them into a fixed 16, if you took those 16 bits and copied them into a 16-bit, you'd have a number between 0 and plus 1, right? And it would be a uniformly distributed number of 16-bit accuracy between 0 and 1. That's pretty efficient. This is a fairly efficient random number generator. It uses what's called a linear congruent generator. It's 1 multiply, 1 add, and a truncation thing. So that's pretty fast. Copying it into a fixed D is very fast. Now you have a number between 0 and 1. You do that 10 times in a row, add them together, you have a Gaussian number to a very good approximation with a mean of 1/2. But let's say you want to make a number between plus 1 and minus 1. What would you do?
Multiply by 2 and subtract 1.
Right. So you could shift this. You could take the rand output, shift it 1 to the left, and then subtract 1. And you'd have a uniformly distributed number between plus and minus 1. How would you do 1.5? Get another random number, shift it right 1 bit, add it to this number, shift it left 1 bit, and subtract 1.5. And now you have a uniformly distributed number between minus 1.5 and plus 1.5. So getting random numbers over a uniform range is quite easy. Because you can easily generate a uniform number between 0 and 1 by copying this number into a fixed 16. What other questions on Lab 3? You can use the new fixed point if you want. I would say in the middle of a lab, it is not a good time to change notation systems. There's no particular speed advantage. They're about the same speed for add and multiply and divide. There's no particular speed advantage. The code is a little cleaner looking. If we look at we can specify a type of accum, so it's underscore accum. I hate leading underscores. I'm sorry. And I even hate more double leading underscores because I can't resolve them from singles. But underscore accum, this defines a new type, which is a fixed type. Then I did the usual fix 16 of my own. Now, when you define a float, I just iterating through floats here. Float 2 to fix 16 gives me the fixed numbers. I just cast the float as an accum, and it becomes an accum data type. So this does the float to accum conversion for me like any other cast in C. Now I can just divide them using the usual notation. So add, subtract, multiply, divide, work as usual. No macros, it just looks right, and it compiles to fairly good code. But you probably don't, like I say, you don't want to change notation now. The example is here if you find yourself nauseated by fix 16, but otherwise don't touch it yet. Out of idle curiosity, I decided I'd see how many cycles these operations in the interrupt service routine actually took, because I thought it was running fairly slowly. And so I modified the DAC DDS example from the target board page to actually turn on the instrumentation in the interrupt service routine. I had put it in there, but in the demo code that I gave you, but I hadn't actually turned it on. So if you don't do no multiply, you merely do the DDS right to the SPI channel and bail out again. The interrupt service routine takes 123 cycles, and the time to get in or out of the interrupt service routine is 23 cycles. If we add one floating point multiply, it goes to 269 samples, 69 cycles, and part of the reason is the context switch doubles to 46 cycles. Why do you think that might be? It has to save the registers that the floating point unit uses.
Okay, but you said it was in or out.
Right. It has to save them going in. It has to restore them going out. So it's symmetric.
Okay, so I still don't really see how like going in would take more time based on the operation inside the ISR.
Because the reason it takes longer depending on the operation inside the ISR is that the floating multiply uses it takes more registers to actually do the multiply, and the compiler notices that. You do 2 multiplies, it takes another 100 cycles. I don't know why that is. That's long. If you do a integer multiply and shift, it's 150 cycles, only up for another extra 20 cycles. And most of that is the context switch is longer because it uses a few more registers. The one floating point multiply, taking this up to 269, explains why people who did 1 or 2 multiplies, floating multiplies, to do the modulation had a failed interrupt service routine. You cannot afford to do floating point in an ISR, in a fast ISR. You have to stick with fixed point or integer arithmetic. And I put the code on here so you can see how it's done, but really it's just that the interrupt handler now has a read timer 2 at the beginning and a read timer 2 at the end, And that gives you all the information you need about how long it takes to do the execution.
I was just going to say that I did do a floating point while my ISR and it worked last lap.
You were running at 100 kilohertz or slower?
100 kilohertz.
At 100 kilohertz, you can make the deadline because you have 400 cycles. If you do 2 multiplies, you come in at 367 cycles, you still make the deadline and the system still operates. The keypad just gets really slow. Did you notice that?
No.
Amazing. Okay. If you stay at 269 cycles, then you're using about half of the CPU for the interrupt service routine, and you probably couldn't notice that.
Yeah, that was what we were doing.
Okay. So what more about Lab 3? How many people got balls bouncing? Good, a few. I like that. It's almost it's like you're parodying the balls bouncing. I like it. Yeah. And how many people have got DMA running? And okay, so good. Okay, was it straightforward?
Yeah.
Yeah, you follow, you know.
It's just chip select that was really tricky. That was it.
Say again?
Just a chip select.
Getting the chip select wired up was, yeah, key. Yeah, okay. Anything else? Let's see. So we have another lecture or so before we're at the halfway point and need to start on Lab 4. So I thought I would talk a little bit more about serial peripheral interface and in talking but on a different example. No, not that page. The PIC32 development board page. I got the chip expander, the port expander working with everything else. So in this case now, the port expander, you want to flip the lights off over there? Thank you. You can see that the port expander is going into the Y port over here. It's no longer going into the A port. And so it's using 7 pins on the Y port. The Y port is a port off of the port expander. And the port expander shares an SPI channel with the DAC. The reason I bring this up is that the DAC is being updated in interrupt service routine 100,000 times a second, which means that virtually always, if you're trying to do some very slow interaction here with the human on the keypad, the DAC will interrupt the SPI sequence for the SPI control of the port expander, which suggests that adding the keypad to the port expander produces a critical section. You know these words, critical section?
You said it last time. That's a part that can't interrupt.
You cannot interrupt. That's right. Yeah, you can't interrupt, and so you have to explicitly lock out the timer 2 interrupt, which runs the DAC while you're doing the keypad read, which only takes a couple of microseconds, so you can do it and not miss an audio sample, or at least only have a little bit of jitter. You probably won't notice one audio sample that's off by 2 microseconds. So this is nice because the port expander is organized as 2 8-bit ports, completely generic, nothing else is attached to them. They have pull-up but not pull-down resistors. You can run them at around 1 million bits a second or so for the 2 ports. And when you get to the point for final projects of needing to run more LEDs or build a big XY decoder with an 8x8 decoder or something, then you can do that off of the port expander. So I want to talk a little bit more about that probably next time. But again, any lingering questions on Lab 3 at this point?
I have a question about the audio. When I know that when we build our tones to that we want to play, you kind of you create a table. But then how do you do that in memory? Is it just
it's an array.
A table?
It's just an array.
Okay.
Right. So if you have a named array like sign table, that becomes the name of an array is a pointer to the array.
Okay.
So you can use that directly as the source of a DMA burst.
Okay.
You can also, as I said, if you make it a constant short array, then the array will be stored in flash, not in RAM. You could store a much bigger array. So if you want the thing to laugh at you, you could put that in flash. And I think I said at one point, down in this VREF as a digital analog converter, I wrote a wave file to header compactor that puts out a C header file as a static, constant, unsigned car. You'd probably want to change this to unsigned short. But you could, and this goes on for 7,000 entries. This is kind of a long, tedious, boring file. But who cares? MATLAB generated it. You can take that file, include it as a header file, and that array will be spit into Flash for you. That could be your sound file. It could be any wave file. How do you generate a sine table in MATLAB?
From an audio.
So you can, if you have any WAV file, audio file, not an MP3 or anything, but just an uncompressed WAV, then this code will generate 4-bit samples. You'll have to modify it for 12-bit samples, but it's fairly straightforward to do that. But you're going to do a WAV to conversion. You also, of course, in MATLAB could just compute a damp sine wave. Sine omega t times e to the minus t over tau will give you a nice damp sine wave, which when you play it will go blink. You could generate that easily as an array, convert it to a header file, store it in Flash. So anything you can algorithmically describe as a mathematical function, you can immediately calculate in MATLAB and store as a header. Otherwise, you have to input it as a wave file. How do you input a wave file? There is you can input an arbitrary sound using audio recorder, which is a MATLAB object that stores the audio in MATLAB as an array. You can then output that as a WAV file and input it back into my converter as a header file. Or you can modify my header generator to to use audio recorder at the input. Maybe I ought to do that just for fun of it. Let's see if I can get the time next week. Okay, I'll be in lab all afternoon. See you there in a few minutes.